Assalamualaikum and salam sejahtera. We from Group K would like to present the TGA and FTIR. This is our group member. First is Hazib bin Afandi. Second is Siti Balkis binti Abdujani. Third is Farisha Nabila binti Hisham. And the last one is Harid Zakwan. This is picture of thermogrammetric analysis or TGA. Okay, for the introduction, thermogrammetric analysis or TGA is an effective method of studying the thermal behavior of material. It measures how a material mass changes with temperature or time under specific general condition. This technique helps determine properties like thermal degradation, oxidation, and decomposition, which are important for understanding thermal stability and composition. In TGA, a sample is placed in a small pan that hangs from a precision balance inside an oven. The furnace can heat the sample gradually or keep it at a constant temperature. As the sample heat, it may undergo processes such as evaporation, dispersion, decomposition, and oxidation, resulting in mass changes. The balance continually record this mass variation, providing value data on the material thermal property. Okay, next, the TGA process. The thermogrammetric analysis or TGA process involves several steps to measure the change in mass of a material as it is heating or cooler under controlled condition. It is a simplified outline of the TGA process. Firstly, with the counterweight 40.7999 milligram before plunging it is the aluminum crucible. After that, place the sample in the aluminum crucible and record its weight. Next is put the furnace in the TGA machine inside one empty crucible and one with crucible. Then close and wait for the result. And lastly, when you get the result, remove the sample. Okay, for the TGA analysis data, firstly temperature range. The x-axis represent the temperature ranging from approximately 4 degrees Celsius to 800 degrees Celsius. Next is mass loss. The y-axis on the left represent the percentage mass loss. The y-axis on the right represent the derivative of the mass loss. And the last one is step in the graph. These two significant steps including to stage of mass loss.
Okay, we go to the detailing application of TGA. For the first is material characterization. TGA help determine the temperature at which material begins to degrade. This information is crucial for ensuring material can withstand the thermal condition they will encounter during use. While analyzing the mass loss at the different temperature stage, TGA can help identify the different components within a material. Second is quality control. TGA is used in manufacturing to ensure the consistency of raw material and final product. Third is research and development. TGA aids in the development of new material with desired thermal properties, providing detailing information on thermal stability and composition. Environment analysis. TGA can help in the analysis of waste material to determine their composition and thermal decomposition characteristic. This is important for developing in-practice waste treatment and recycling process. Next is a food industry. TGA can determine the moisture content in food product, which is crucial for quality control and safe life prediction. Last, polymer and composite. TGA can analyze the thermal stability of fiber and metric material in composite, which is important for application requiring high strength and thermal resistance. Okay, we go to the functional of TGA for the first polymer industry. In the polymer industry, TGA can help manufacture ensure that their product maintain their integrity under heat stress. By analyzing temperature and decomposition pattern, it help in optimizing formulation to improve performance and durability. Second is pharmaceutical. In pharmaceutical, TGA ensure the both active ingredient and active can withstand storage condition without degradation, which is important to maintain drugs efficacy and safety. Next is material science. Material science use TGA to characterize the thermal behavior of various material, aiding in development of material with desired thermal properties for specific application. For environment science, TGA help environment scientists understand how waste and pollutant break down under heat, which is important for creating effective recycling and disposal method. Next is food industry. In food industry, TGA ensure that product maintain their quality and safety by accurately determining the moisture level and stability of additive under thermal condition. This as is building material. TGA is essential to ensure the durability and safety of building material by analyzing their thermal stability and decomposition characteristic. 7 is comestic industry. In comestic industry, TGA help in maintain product quality by verify that ingredient and final product can withstand expected storage and use condition without degrading. In conclusion, TGA is effective technique for studying the thermal characteristic and decomposition behavior of candle wax. The TGA curve provides valuable information on weight loss and at different temperature, revealing the wax thermal stability, composition, and decomposition process. Understanding the influence of environmental factor future actions analysis. Coupling TGA with other analytical technique like MS and FTIR offer a more comprehensive understanding, beneficial for further research and practical application. Thank you.
Introduction for transform infrared FTIR spectroscopy is a powerful analytic technique used to identify organic, polymeric, and in some cases inorganic material. The method involves measuring the infrared intensity versus wavelength or frequency of light. FTIR is widely utilized in both qualitative and quantitative analysis, offering several advantages over traditional dispensive infrared spectroscopy. FTIR process: first, prepare the sample, clean the stage with solvent, place the sample on the stage, place the mounted section into the FTIR spectrometer, check the baseline and adjust if necessary to obtain clear spectra, accurate spectra by measuring IR absorption at different wavelengths, analysis spectra with software.
Analysis data. For graph 1, the FTIR spectrum of untreated cellulose shows characteristic peaks at specific wave number corresponding to different functional groups. Graph 2, the comparison between treated and untreated cellulose sample shows a reduction in the intensity of the OH peaks in treated sample. This suggests the removal or alteration of hydroxyl and carbonyl groups due to the treatment. Graph 3, the detailed spectrum of treated sample shows consistent peak with those observed in the untreated sample, confirming the presence of cellulose and other functional group. Graph 4, the cellulose-specific spectrum shows peak at 1100 cm, which is CO stretching, and 896 cm beta-glycosidic leakage, further confirming the structural component of cellulose. Graph 5, the overlay of spectra from the multiple samples show consistent peak for OH, CO, and cellulose across different samples. This indicates a reliable presence of cellulose and similar functional group. The post-treatment spectrum show a reduction in the intensity of OH and CO peak, while the cellulose-specific peak remains stable. This indicates that the treatment affects other components more than cellulose. Graph 7, the spectrum of complex mixture show multiple functional groups, confirming the presence of cellulose as a significant component along with other compounds. Graph 8, the spectrum showing post-treatment changes indicate variation in peaks intensity, particularly for cellulose-related peaks.
First is identification of functional group. FTIR machines are capable of identifying various functional groups in a molecule by measuring their unit absorption peaks. Second is qualitative analysis. FTIR spectroscopy is used to qualitatively analyze a sample, determining the percent of absence of specific compound or functional groups. This helps in identifying unknown substance by comparing the sample spectrum with reference spectra. Next, quantitative analysis. By analyzing the intensity of absorption peaks, FTIR can be used to quantitative analysis. This function helps in determining of concentration of specific component in a measure. Next, crystallization of material. FTIR is widely used in material science to characterize polymer, nanomaterial, coatings, and other materials, and help in understanding their chemical composition, crystallinity, and structural properties.
Next, detailing applications of FTIR spectroscopy. First, we can use in material science. For example, polymer analysis. FTIR is extensively used to study polymers. It helps in identifying polymer type, detecting additive, and monitoring polymer degradation. Next, pharmaceutical industry. For drug development, FTIR is used to identify active pharmaceutical ingredients and excipients in drug formulation. Next, environmental monitoring, air quality analysis. FTIR can detect and quantify pollutants like carbon dioxide, methane, and other greenhouse gases in the atmosphere. For food and agriculture, food quality and safety, FTIR is used to analyze the composition of food product, ensuring quality and safety by detecting adulterant and contaminant.
In conclusion, FTIR spectroscopy is a powerful and versatile tool that provides comprehensive insight into the chemical and structural properties of a wide range of materials. Its ability to deliver precise, reliable, and detailed information make it invaluable for research, quality control, and industrial application, thereby advancing scientific understanding and technological development across numerous disciplines.